Welcome to MathCabin.com. In the previous videos, we discussed how to find the total number of upright squares in this 8 by 8 square. Okay? Now when I say upright, what you probably saw in those videos is when you have vertical and horizontal sides of the square, right? Speaking of vertical and horizontal, right? But we didn't discuss the tilted squares in which, let's say, your vertices may not be connected by horizontal or vertical lines. So basically what I mean is something like this. That would also be a square, right? So we didn't calculate how many of these square types can there possibly be as well besides the upright squares. So here's the way to go. So we're going to start with a smaller square. For the sake of developing a formula, we're gonna work on the 5 by 5 square. Okay, and as soon as we get the formula, we're gonna use that to find the total number of upright and tilted squares in this square. Okay, so we already know the formula for the upright squares. I'm gonna write it down, but we don't know the formula for the number of tilted squares, right? So we're gonna have to go piece by piece in determining that. Okay, so first, let's draw some vertices. So we can take a look at this kind of square. So if you connect all the vertices, you'll see that it's going to be a square with all equal sides. So now, how many different squares of this type can fit into this 5 by 5 square? We know that we can go by the movements, okay, of the outer right and outer bottom vertices. 1, 2, 3, 4 movements down, and then 4 movements to the right. Right, so we know that we can express it as 4 by 4. Okay, and notice that 4 by 4, just like I used in the previous video, product rule accounts for all possible 16, the total number of 16 possible movements for this square within this 5 by 5 square. Now, how many squares of this type are we going to have? I want you to understand something, that it also requires your understanding of symmetry. Notice that symmetrically, so this, as you can see, is symmetric, this square, with respect to the midline here that goes through the center of this 5 by 5 square. So we also have to account for these as well. It's the same size. Notice that these are the same sizes. So now how many movements of this type are we going to have? We're going to have 1, 2, 3 versions going down, and then 3 versions going to the right. So we're going to do 3 by 3 and also multiplying it by 2. So this is the square now we're talking about. So that's a symmetrical version with respect to the midline going to the center of this 5 by 5 square. We're going to do 2 times, and then let's see how many movements we can have at this time. 2 down and 2 to the right, right? So we're going to do 2 times 2. Notice we have a square again. Now it has only one such square with this tilt. But don't forget that there's also the symmetric version of this. That's a symmetric version of this one. It's going to be 2 times. Notice this one is static, right? It doesn't move to the right or left, right? It's just basically inscribed, so to speak, right? So it's going to be one version down and one version to the right. Now notice this is the same type, speaking of the orientation, it's the same type as the smallest one that we started with, the 4 by 4 ones. And notice that symmetry didn't play a role when we counted that, because symmetrically it would be the same type of position. Okay, so symmetry would not affect the 4 times 4, the 16 of the smallest ones that we started with. Notice this one is just like the first 16 we started with, because symmetry doesn't play a role here, because the center will still be the same, and then the position of the sides will be the same from the right side facing to the left. We know it's 2 versions down and 2 versions to the right. So it's going to be 2 times 2. We didn't yet talk about this one yet, and again there's symmetry involved, so that's the symmetrical counterpart. So there happens to be exactly 2 of these because it is already inscribed. Okay, so we're just going to write twice the 1 times 1, right? Twice because there's a symmetrical one and it's inscribed, so it's just 1 times 1 because there's no room to go down or to the right. These are the 6 sizes that we've explored using these products. There are no more sizes that are possible within this 5 by 5 square. All right, so now that we have these 6 sizes, we can go ahead and try to derive a formula just setting the n being equal to 5. Okay? So notice that the n stands for the number of rows and the number of columns. And since it's a square, the n value is going to be the same. The number of rows is 5, the number of columns is also 5. We know from the previous video that the number of upright squares is going to be using the formula. So we know that n minus 1 times n minus 1 product, there's only one product like this, right? So it's just going to be n minus 1 times n minus 1. Now we have n minus 2. How many products of this we have, right? We only have 2. Right, so we're going to write 2, n minus 2, n minus 2. Now how many n minus 3 products? We have 2, and then we have another 1. So it's going to be 3 altogether. And then finally n minus 4. How many of those do we have? 2 and 2. So that's 4. So 4n minus 4, n minus 4. That tells me that there's a pattern because n minus 2, that 2 there happens to coincide with the coefficient in the front. 2, n minus 2, 3, n minus 3, 4, n minus 4. 1, n minus 1, right? Because you don't see that 1, but you know that 1 exists theoretically. 1 times n minus 1 squared plus 2 n minus 2 squared plus all the way until theoretically, instead of that 2, we're going to have the highest possible value, whatever that value that stops this sequence. Right? So we know we can name it as k, because we don't know what that number in the front is going to be. It's the highest number, highest integer number, so it's going to be n minus k squared, with k is less than or equal to n minus 1. If it's exactly the n value, it's going to be 0, right? And we don't want any of the terms to be 0, so it has to be 1 before last, n minus 1. And then we can use the summation notation. We can write it as from counting from 1, the k value being 1 here, all the way to n minus 1 being the last one. And here we're going to have k times n minus k squared. N minus k squared can be expanded. I'm placing the n squared on the left side of the summation, right? I'm just using the summation rule for the sum of the first n minus 1 terms, from 1 to n minus 1. Okay, so that's going to be n minus 1 times n divided by 2. And n squared, again, I'm placing it to the left of the summation symbol, which is just going to be multiplied. So then I'm going to have minus, so I'm going to place now 2n outside of the summation. So the k will be multiplied to the k, so there's going to be a k squared now. So how many k squared terms will be from 1 to n minus 1? And that's going to be what? That's going to be taking the n minus 1, the highest there, then 1 higher, which is n, and then don't forget it's going to be twice the highest term, n minus 1, and then plus 1, okay, plus 1 according to that formula, and then close the bracket and then divide all that by 6. I'm going to write the first n cubes formula so that you will follow it in case if you forgot it. It's going to be n times n plus 1 divided by 2 squared. All right, so that's a formula for the first n cubes. So in this case, we're talking about the first n minus 1 cubes. And why cubes again? Because notice k squared multiplies the k, and there's no n to take out, right? So it's just going to be k to the third. So basically, instead of n here, you should write n minus 1. I'm going to combine this. Notice that this is the number of upright squares, right? So I'm just going to distribute everything here. And then here we're going to have n to the fourth, right? Starting from the first term of the tilted sum that we found. Minus, and then here it's gonna be crazy here, but you should just write, and then plus, and then here we're gonna have what? Don't forget that it's gonna be squared. The least common denominator should be 12. So we're gonna multiply all of these terms by 2, all of these terms by 6, all of these terms by 2, and then all of these terms by 3 in order to have a 12 there, right? So we have to have 12 on the bottoms of all of these fractions. All right, so if you combine the like terms, get rid of the terms you don't need as a result of that, it's going to be just 4 terms on the top. Right? So that's the golden formula that will tell us the total number of squares, which means upright and tilted, in any size and square, right? Because this accounts for any size and square. So we can go ahead and use this to find the 8 by 8 square size and to see how many of these types of squares and the upright squares exist in that using this formula. So now that we have this formula, let's go ahead and plug in n is equal to 8 into this and find the total number of upright and tilted squares here. All right, so if you do this carefully, you should get 540. Okay, upright and tilted squares. Okay, thank you so much for watching. I hope this was fun and helpful. See you in my next video.